And the last step takes the solar radiation from the previous video, takes the solar pump power in kilowatts from step 2, and now works out the pump performance. We're not talking about a specific pump, it's just really trying to understand it. And more importantly, what variation can we expect? Oh, again, the loading function is what we talked about from step 2, and some efficiency and flow rate. Now, flow rate is something that every pump has. So the more power it has, the more flow rate it can get. A new concept here is we want to now determine the overall efficiency and the overall uncertainty of the electrical power that comes out of the pump, right? So what does that mean? It means the efficiency of a pump can be lost in many ways. So efficiency, just like the panel, as you can see, right? The panel is inefficient, then the pump is inefficient. So all of that can really make a really inefficient system if you're not careful. So noise, specifically Gaussian noise, it allows you to get a variation of what we call white noise, which allows you to get more realistic data. Why is that important? Realistic data is trying to mimic the uncertainties that you have in the world, right? Everything has some level of variation, and that's what Gaussian noise really came about, where the concentration, depending on how many samples, can really give you the standard deviation across specific spectrum of noise. And the noise that you're able to use here is trying to get to understand how much noise is around the electrical power, how much uncertainty do we have around the electrical power. So it takes a random seed and then randomize it across the full set of the power matrix element, and then compute the noisy power based on adding the power, which is non-noisy, to the actual noise, and then ensure that there are no negatives by doing the max of it. Now, this is a panel area. It comes from the panel range, right? Now, that was stored in electrical power contour. This is a range between 1 and 10 meters squared. That now can be used as a means to look at the overall design of how much flow can I get through the efficiency, and also through understanding the noise characteristics or uncertainty. Now, why is this important? It's worst case and best case, so that you're able to work within the uncertainty and not over budget or under budget. So now another plot, which is a plotting function, which is given here, is the y-axis. A very interesting way of plotting two different kinds of data set that have the same x-axis, i.e. time in this case, but gives you some correlation without having to plot into contours and colors, and it still allows you to interrogate the numbers. And in this case, this saves a lot of things. So I'll put it here and then press run. All right. So what is it showing? It's showing, like I just said, right? It's showing on that there's two legends or two labels on either side of the y-axis while they're using the same x-axis, in this case, time. And what you're able to see very clearly by using this way of plotting, you're able to see the electrical power on the left, and you're able to see the water flow rate on the right. Why is this correlating? Basically, it's trying to show that at some point during the day, which is around 12 or between 10 and 3, you are able to get roughly the highest electrical power through your pump, but also the highest flow rate. But it's not always the case. This is all down to noise, right? The power to flow rate ratio might be higher or lower depending on the time of day. You will not always get the same flow rate for the same power because of the noise and the uncertainty that goes with the efficiency of your motor and of your pump. And this is predicted, or this is assumed, by using random noise which embeds uncertainty. This is engineering 101. I'm assuming that I will have some uncertainty in my system, and I need to take into account that uncertainty, that I don't just switch on my pump at 12 because I might not get the same water flow rate. Potentially, I will get it later, or earlier. So what do? Switch it on between 10 and 3. So with that in mind, this concludes the segment of this course regarding MATLAB and MATLAB plots, MATLAB contours, MATLAB saving and loading, and more importantly, the understanding of how do we start translating a solar powered system into a MATLAB environment and eventually into a Simulink environment.